In this notebook, we'll be going over the basics of the Matplotlib library, which is a powerful tool capable of producing complex publication quality figures with fine layout control in 2 or 3 dimensions. While this is an older library, so many libraries are built on top of it and use its syntax. What this is doing is it's saying that we want the appropriate backend to make our figures appear inline in the notebook. As usual, we're going to import Pandas as PD and NumPy as NP. We're going to import the Matplotlib.ipynb module as PLT. The next thing is we're going to import the Seaborn library as SNS. This is a wrapper of Matplotlib. The next thing is we're going to import a dataset into a Pandas data frame. A good practice is to view the first 5 rows of a data frame. This is important as it's good to see what kind of data you're working with and to see that the data was correctly imported. What this code is doing is I'm selecting the month column as a Pandas series. From here, I'm looking at the values attribute, and what this will give us is we're converting this Pandas series into a NumPy array, and we're setting all this to the variable month_number. And we're doing something similar for the variable interest paid and principal paid. And the rationale for converting our Pandas data frame columns into a NumPy array is this will make it easier for graphing. We're going to plot month number on the x-axis and principal paid on the y-axis. And as a reminder, if you don't know what a method does, you can always use the inbuilt help function to find out. And what this is showing is that our first argument will be our x-axis and our second will be our y. This is not the prettiest plot, and we'll get into how to make things a little bit more aesthetically pleasing throughout this lesson. But first, let's go over how to plot another line on the same graph. We're going to call plt.plot again, and this time we're also going to graph the principal paid column. This next section goes over how to select the most appropriate aesthetic style for a figure. This is because the default style may not be the most ideal or aesthetically pleasing. We have a couple of different style choices that we can utilize, and I'll show you a couple. We are currently using something very similar to the classic style, so this will not make our plot look much different. This is what the 538 style looks like. As you can see, we have grid lines now. If you've used the R programming language, there's a good chance you've used the library ggplot, and Python has a way to make your plots look similar. There's also the Tableau colorblind. And here is the Seaborn style. The next step is to go over how to change everything in our figure and not just rely on default styles. This notebook goes over how to change the marker type as well as a color for your plots. As usual, we have to import the libraries that we want to use. We're loading our data. This table here is just showing a couple different common marker types. We have a point marker, pixel, circle, etc. And what we're going to do now is we're changing our marker type and our marker size. And with Matplotlib, if you don't know what something does, I highly encourage you to play around with it a little bit. You can also change the color. And there's a C parameter which accepts strings. tuples, as well as hexadecimal. So we have blue and black. We're doing the same thing, but we're doing it through hexadecimal instead of specifying a color through a string. And you can also do this using tuples. In this notebook, we'll be going over a more difficult part of the Matplotlib library, and this is understanding the MATLAB style syntax and the object-oriented style syntax for the Matplotlib library. As usual, we're importing the libraries that we want to use. We're loading data. A brief note about the two different styles of syntax. The MATLAB style is a scripted interface designed to feel like MATLAB. This is where Matplotlib maintains a pointer to the current active figure and sends commands to it. So far, we've used the MATLAB style syntax. There is the object-oriented style syntax, and this is more often used in situations where you want more control over your figure. A very, very important note is that you can and often will have plots that will be created through a combination of the MATLAB style and object-oriented style syntax. So as you see here, this is the MATLAB style, and this is what we've been doing so far. This code is utilizing the object-oriented style syntax. This first line, we're creating a subplot of one figure, and we're tuple unpacking where we have a figure object and an axis object. From here, it's very similar to the MATLAB style. This code utilizes a combination of the object-oriented style syntax and the MATLAB style syntax. This notebook goes over how to add titles, labels, and limits to your plots in both the MATLAB style and object-oriented style syntax. As usual, we have to import our libraries. We have to load data. Here is our plot in the MATLAB style syntax without adding limits, titles, or labels. We can change the x limits and y limits. To do this, we can use the xlim method. We're saying that we want the left side of the figure to start at 1, and we want the right side to end at 70. We can also set the y limits by specifying we want the bottom of this graph to start at 0, and the top to end at 1000. For this particular figure, I'm not necessarily trying to make it more functional, aesthetically pleasing, or pretty. I'm just showing you that you can modify it. We can also add x labels and y labels to our plot. To do this, we can add an x label by using the xlabel method and specifying the string of our x label. And to add a y label is very similar. We just use the y label method. We can also add a title to our plot, and to do this, we can use plt.title. For any x label, y label, or title, we can also change the font size. In this case, we're making it bigger. And similarly, we can also change the tick font size. And as you can see here, our ticks are bigger than they were before. We just went over how to add titles, labels, and limits using the MATLAB style syntax. We can also do the same thing using the object-oriented style syntax. Here's our plot without adding or changing anything. To set the x limit and y limit using the object-oriented style syntax, we can use the set_xlim method, and for the y limit, we can use the set_ylim method. To set the x label and y label, we can use the set_xlabel method and the set_ylabel method. Additionally, if you want to add a title, you can just use the set_title method. And of course, we can change the font size. The reason why I'm going over the MATLAB style and the object-oriented style in such detail is that oftentimes, if you need help, you'll go on Stack Overflow, or you'll read a book, or find another resource, and people will mix up the styles of syntax. It might be a bit confusing. So this is just here as a resource for you. In this notebook, we'll go over how to add grids to your plots. As usual, we're going to import the libraries that we want to use. We're going to load data. Here's our plot without grids. To add grids using the MATLAB style, you can use the grid method. If you want to only add horizontal grid lines, you can do this by specifying axes equals y. Similarly, you can only add vertical grid lines by using axes equals x. And this code is just showing you can change the color of your grid lines, transparency, and line style. You can also add grid lines to your plots using the object-oriented style syntax. Additionally, you can also only add horizontal grid lines, vertical, as well as change the color, transparency, and line style. Additionally, if you find setting grids manually to be tedious, you can use a Matplotlib style that has grids by default. For example, Seaborn does. This notebook goes over how to add legends to your plots. As usual, we're importing the libraries that we want to use. We're loading data. Let's first go over how to add legends using the MATLAB style syntax. You can do this by using the legend method. You can specify where on the plot you want your legend to be. And as you see here, the legend is overlapping the graph right now. So let's try center right. This looks a bit better. Keep in mind though, you can also add a legend outside the plotting area. And for this, I'm specifying that I want it a little bit to the right of the plot. Additionally, you can also utilize the object-oriented style syntax. In this notebook, we'll be going over how to save plots to files. This is actually a very important notebook, as oftentimes what's outputted in a Jupyter notebook is not exactly how it's saved to a file. As usual, we're going to import the libraries that we want to use. We're going to load data, etc. To save my plot to a file using the MATLAB style, I'll be using the savefig method. I'm setting the DPI to 300. You can think of this as a kind of resolution. And I'll be saving the image in my images folder. And what you see here in the notebook is not necessarily what you'll be saving. So let's look at what we saved. As you can see on the right side of your screen, it looks like the legend is cut off. Now let's go over a solution to this. One way to handle a legend being cut off, or any other part of your figure being cut off, is to utilize the TitlesLayout method. And it's just tit_layout. And as you see here, it looks like nothing is cut off. Additionally, you can also save plots to files using the object-oriented style syntax, and it's just the save fig method. If you encounter the same problem as before, you can utilize the TitlesLayout method. This subplots notebook goes over how to create subplots using Matplotlib. Subplots are often useful to compare different subsets of your data side by side. To demonstrate this, we're going to visualize images side by side. As usual, we're going to first import the libraries that we want to use. We're going to load data. This dataset is the digits dataset from scikit-learn that I conveniently arranged into a CSV file. The data consists of pixel intensity values for 1,797 images that are 8 by 8 pixels. This means that the dataset has 64 total values per image. Each image is labeled with a number from 0 to 9. This particular dataset will be loading into a Pandas data frame. Let's look at the first 5 rows of the dataset. As you see outputted, we have column names that start from 0 and go all the way up to column name 63. Additionally, we have a label column. This is what the image is supposed to be of. So this first row should be the pixel intensity values for a digit that looks like a 0. This one should be a 1, a 2, a 3, etc. What this code is doing is getting all the column names for every column except for the label column. What this line of code is doing is I'm getting all the values for the first image, which should actually be a 0. The goal of this loading data section is to show you what the images actually look like before we try to create subplots. What this code is doing is it's showing you the shape for the NumPy array. Remember that image_values is the data for the first image. The images are 8 by 8 pixels. It's important to keep in mind that just because a dataset is stored in a certain way doesn't mean it was meant to be viewed that way. Accordingly, we're going to reshape the data from this to an 8 by 8. As it's not easy to understand pixel intensity values by looking at an array, let's visualize the image. To do this, I'll be utilizing the IMShow method. What this code is doing is it's meant to show you how the dataset would have been shaped if you didn't reshape it into an 8 by 8 image. Doesn't look that clear. The code below is plotting 5 different images into one plot. And as you see, we have 5 different images, all in one row and 5 columns. If you actually look at the code itself, you'll see that we have an awful lot of replicated code where we call the subplot method. We say that we want 1 row, 5 columns, and this is the first plot, this is the second plot, third, fourth, and fifth. Since most of these lines of code are very similar, we can accomplish the same result by using a for loop. The goal of this Heatmaps notebook is to show the importance of choosing an appropriate color palette. A heat map is a graphical representation of data where values are depicted by colors. Heat maps allow you to easier spot where something happened and where it didn't. Consequently, what we choose for a color palette is important. 2 types of color palettes are sequential, and this is appropriate when data ranges from relatively low values to relatively high values. There's also qualitative, and this is best when you want to distinguish discrete chunks of data that do not have inherent ordering. The data that we will use to create a heat map is for a confusion matrix. A confusion matrix is often used to tell you where your predictions went wrong. In the case of the images above, it is derived from predicting labels for digits from 0 to 9. As usual, we're first going to import the libraries that we're going to use. Here's the data for our confusion matrix. To create a heat map using Matplotlib without a wrapper involves quite a bit of code. So right now I'm going to mention a few flaws that Matplotlib definitely has. One of the first ones is that Matplotlib defaults are not ideal. There's no grid lines by default, there's a white background, etc. The library is also relatively low level. So in this case, for heat maps and anything else complicated, it involves quite a bit of code. And third, there's not perfect integration with Pandas data structures, though this is being continuously improved. Here's the code to create a heat map for our data using pure Matplotlib. And as you might be able to tell, this is still not a perfect plot, as the default still has our text in black, and it's hard to distinguish between this dark blue and this black 51. One way to avoid using so much Matplotlib code is to use a wrapper of Matplotlib. A very popular wrapper of Matplotlib is Seaborn. And since Seaborn is a wrapper of Matplotlib, you'll often see that you can use Matplotlib syntax to adjust the final plot output. And in the case below, the Matplotlib syntax adds X labels and Y labels. In the code here, we're utilizing the heatmap method. We're inputting our NumPy array. We're saying that we want annotations. If you're not sure what annotations equals true means, try setting this to false and seeing the output. And we're saying that we want our color map to be blues. For my particular version of Matplotlib, I have things cut out on the top and the bottom. And while you may not, I encourage you to follow along this part of the video, as it's good to understand how to debug problems if they occur. So the way I tackled this problem is I Googled Seaborn heat map top and bottom cutoff. I looked at the issue on GitHub. I saw that someone else had a similar issue. It turns out that some error was introduced in a version of Matplotlib. So I looked at some of the solutions that people had. I saw that a lot of people use this solution. I copied that. I added that code, and the error was gone. Additionally, if you like to utilize a pure object-oriented style syntax, there's another solution available. And as you see here, we're assigning the heat map to an object axis. We're then getting our current by limits. And then from there, we're adjusting the bottom of the figure and the top. And it's again important to emphasize that there's a very good chance that you won't get this error, as you're not using the same exact version of Matplotlib that I am. The reason why I'm showing you this is to show you that sometimes you get errors, and that you can oftentimes solve your problem by Googling them or asking for help, either through the class discussion or through Stack Overflow. And what the code here is doing is it's showing you a qualitative color map. And this might not be the best choice for our data, as our data has ordering, and this color map doesn't.